So, welcome to Multivariable Calculus, Section 1, Lecture 3. So today we're going to be talking about the cross product. What class do you think would have been really useful to have taken before today's lecture? Yes? Linear algebra. It's almost always linear algebra or real analysis. Today the answer is linear algebra. And if we had taken linear algebra, we would have had a much better understanding of what's going on and being able to just do one or two special cases. All right, so chalk is terrible today. All right, so the cross product has some very interesting interpretations. What I want to do is very similar to what we did when we did the dot product, is I want to start off with a special case and then use that to motivate geometrically what's going on. What's really lurking in the background for the cross product is this notion of a determinant. How many of you have seen determinants before? Okay, how many of you have not seen determinants before? Okay, so a quick review of determinants. So say we're trying to solve a system of equations, ax plus by equals, say, I'll do maybe u, and cx plus dy equals v. No, it's not tracking today. The new system is supposed to arrive yesterday. All right, you can write this in matrix form, A, B, C, D, acting on x, y equals uv. So how many of you have not seen a matrix equation like this before? Okay, so it's okay if you haven't seen this before. This is a way to motivate a little bit of what's going to happen in linear algebra. One of the purposes of linear algebra is to provide a framework to do algebraic operations in a clean way. So when you've had equations like this, one way you've learned how to solve it is maybe you solve for x in terms of y, then you substitute that in here, and then you have one equation with one unknown, you solve it, and then you go backwards. So linear algebra gives you a bunch of techniques to solve stuff like this. But it's not always possible to solve equations like this. So if you think about this, if these two lines are parallel, then they're either identical, lying one on top of the other, or they're separated. If they're separated, you can't simultaneously solve them. So for instance, if I'm trying to solve x plus y equals 4, and x plus y equals 8, good luck. Not going to happen. Right? What if I tried to solve x plus y equals 4 and 2x plus 2y equals 8? How many solutions will this system have? Infinitely many. So amazingly, when you have systems of equations like this, you'll either have 0 solutions, 1 solution, or infinitely many solutions. There's never just 2, just 3, just 4. And what's going on here is if the two lines are the same, well, then any pair that works for the first works for the second. You want a quick way to determine when a system of equations will have a solution. And so when we have square matrices like this, the determinant gives us a really good way. And the geometric interpretation of the determinant is in a 2 by 2 matrix. It's going to be the area of the parallelogram created by the vector AB and CD. So here's AB, here's CD, and I'm going to get a parallelogram like that. And the determinant of the matrix ABCD, and we often write this as ABCD with vertical lines, is defined to be AD minus BC. Now, I can define anything I want in mathematics. I could define this with a plus sign. I could define it as AB plus CD. It's what's a good thing to define. Why is this reasonable? Okay? Well, if we try to look at what's going on, what direction would you love AB to be in? Along the x-axis. So if we try as our special case again. All right, now it's beginning to swivel. All right, so if we try as a special case, AB is along the x-axis. Maybe it's A0. And here is now CD. So how do we calculate the area of a parallelogram? Why?
Because you can draw like a perpendicular line.
Okay, so I can draw a perpendicular line. So why is it base times height?
I don't know the
if you drew those lines on the outside instead.
Like over here? Okay.
And then the same on the other side.
Okay. From here going up or from here going down?
From there going down.
Okay. You're very close. You made it a little bit too big.
This is just one of them.
So you want to have this one going up.
Oh, right. Okay.
So now if you look at it, this triangle here is the same as this triangle here. Why? Well, these are two pairs of parallel lines of the same length. So going back to our old geometry days, if this angle is theta here, this angle here would also be theta. And then this angle here would be 90 minus theta. This angle here would be theta. These two triangles have the same hypotenuse, and they clearly have the same side here. And now you have to remember all those different ways of combining the letters A and S for those triangle laws, the angle, side, side, which ones are valid. Well, here all the angles are the same, and I have two sides. So I have side angle side, which is valid. So this triangle is actually of equal area as this one. So if I just move this one over here, I now have a rectangle, base times height. So that's the proof that the area of a parallelogram is base times height. So now, if this is CD, what would be the height of this?
D.
It would just be D. So the height is D, the base is A, so the area is AD. Okay? So this is a start to the proof. And it shows you that at least this term is right in this one special case. But what's going to go on in general? So I will try to resist the temptation to go too much into linear algebra, but it's not bad to see some of it now so that when you take a linear algebra class, as I hope many of you will, I've seen that before. I remember when Professor Miller was babbling about that now. Okay, that's where it all leads to. And so the idea is what we can do in 2 dimensions, we can hopefully do in 3 and 4 and 5 and higher. So in here, we're trying to find the area of a parallelogram generated by these 2 vectors. The next thing is, well, what if I had 3 vectors in 3 space? That'd be a volume of a parallel pipette. What if I had 4 vectors in 4 space? I don't know what you would call that object, but there should be some kind of hypervolume. What do you think would be the easiest choice if I give you AB for CD where you would absolutely know what the area is? Yes? 0. So if I take C and D to be 0, 0, really easy. And you can see in the formula that the determinant, which is just the area, would be 0. So this is the area of parallel pipette. Parallelogram. Parallel. I'm misspelling it right now. I'll say I'm still medicated. Now, this is actually a signed area, because if I switch the order of these 2 rows, I will actually switch things. So let's see what would happen if we wrote it in the other way. If I have now CD, AB, if I do it in this order, I now get CB minus AD, which is negative AD minus BC. So it's actually giving you a signed area. This is very similar to calculus, when you calculate the integral under the curve, it's positive if it's above the x-axis, it's negative if it's below. So one good choice of CD is 0. There's another yes?
I just have a quick question about is the reason the area of the parallelogram we found just AD instead of AD minus BC because our B was 0?
Our B was 0, exactly. And that's why things come out so nice.
Okay.
So trying to motivate, very similar to the dot product, let's look at a simple case in one direction. If we knew linear algebra, we could then say by applying rotation matrices, we're done. Sadly, we don't know rotation matrices. So we get to spend more time doing algebra. There's another choice of direction CD where the area of the parallelogram will be really easy to compute. Any thoughts on that choice?
1, 1.
Not 1, 1. Yes?
AB?
AB, or 2A, 2B, or 3A, 3B. Or, as long as CD is in the same direction as AB, it's going to be easy to compute. Again, right now we haven't proven this formula. I'm just claiming this formula gives you the area. But I'm saying, well, what if I just give you two vectors and ask you, what is the area of the parallelogram they generate? If they're both in the same direction, they generate a line. What's the area of a line?
0.
0. And so if we now try, say, A, B, and I'll do R times A, R times B. So the second vector is a multiple of the first. I would get A times RB minus B times RA, which is just 0. So in the special case where the second vector is just a multiple of the first, we see that the area is 0. All right, so let's try to go back to the cross product. So I will state the formula. When you first see it, the formula looks absolutely absurd. All right, so if V is V1, V2, V3, and W is W1, W2, W3, then V cross W is the vector V2, W3 minus V3, W2, comma, V3, W1 minus V1, W3, comma, V1, W2 minus V2, W1. Okay? Again, I can define anything I want. The question is, when is this useful? It turns out the cross product has a lot of really nice properties. It turns out V cross W is perpendicular to V and perpendicular to W. And V cross W is negative W cross V. So how do you think we would prove those results? Which one do you think is easier to prove? Yes?
The perpendicular one?
The perpendicular. Okay, so how would you prove the perpendicular one?
Maybe try like an extreme, like equal to 0 or something.
How would you do that? Well, so what does it mean for two vectors to be perpendicular? Right.
The angle between them is 90.
Okay, so how do you tell if the angle is 90?
Oh, you have to do the dot product?
The dot product. So plug and chug. Just compute V dot V cross W. Do algebra, and you get 0. It's very unenlightening. You know, you'll get V1 times this, plus V2 times that, plus V3 times that, and then you just go through and you just see that all the terms cancel. This is a proof. It is not an enlightening proof. It looks like a magical fact. And so I will try to give some explanation later today as to why that is the case. Okay, it's true, we can now use this. If there's time at the end of class, I will talk about Morley's theorem and a bet I made many years ago where I believe I have the longest proof on record of a result. My proof is about 47, 48 pages of complete calculation. The best proof is a paragraph. My proof is extremely unenlightening. It was a result of a bet. So we have this fact. Now the other fact, V cross W is equal to negative W cross V. How would we prove that?
You could actually compute negative W cross V and just prove
Yeah,
that it's the negative.
exactly. Just compute both sides. Or you can see that if you flip the orders of things, what will happen? And so just go through and switch the orders, compute, multiply by -1, and show that they're the same. So these are not really enlightening proofs. These are really follow-your-nose proofs. If you think back to the proofs from Calc 1, how do you prove the product rule, the quotient rule? A lot of these rules come down to you have to very cleverly figure out a way to add 0, or a clever way to multiply by 1. Here, it's just do the algebra. So in some sense, these proofs are actually easier than the proofs from calculus. If you remember the chain rule, you have to multiply by 1 in a clever way. If you remember the product rule, you have to subtract 0 in a clever way. We don't have to do stuff like that. We just have to roll up our sleeves. Okay. How many of you are excited about memorizing a formula like this? Good. I am going to show you a shortcut that works. This is a really bad shortcut in some sense, in that I'm doing a lot of illegal things, but it's been accepted by the math community and by the physics community, so I will teach it. It's a really good mnemonic. It mixes up various things that should not be mixed up, but, all right. So again, it would be really helpful to know linear algebra. It turns out that the way you calculate determinants of bigger matrices is you break them down into determinants of smaller matrices. And there's this subject called expansion by minors. I am not going to get into that. I am going to show you a trick that happens to work for 3x3 matrices and does not work beyond that. So do not try to do this trick on 4x4 matrices or 5x5. Okay? You should think of the 16 over 64, the 49 over 98, the 19 over 95. Sometimes these things work. All right? If I give you a matrix A, B, C, D, E, F, G, H, I, and I want to calculate the determinant of this 3x3 matrix. How many of you have calculated determinants of 3x3 matrices? How many of you know the two-column trick? You write the first two columns again, A, D, G, B, E, H. You then go diagonally, and the downs come with a plus sign, and the ups come with a minus sign. And you get AEI plus BFG plus CDH minus GEC minus HFD, HFA minus IDB. How many of you have seen this before? Okay, a few people have somewhat seen this. Okay, good. It does not work in higher. But it's a nice way to remember the formula for the determinant of a 3x3. Okay. And so this is not good at all. So now, this is where we can get a formula for the cross product by using our formula for the determinant. Now, the problem with the determinant is we need three 3x3 vectors. For our cross product, I've got v1, v2, v3, w1, w2, w3. I only have two vectors. I need three vectors. Well, the cross product also outputs a vector, not a number. The determinant is outputting a number. So the trick is to put in the I vector, the J vector, and the K vector. So remember, the book likes to use I, J, and K for the unit vector in the x direction unit vector in the y direction, unit vector in the z direction. This is not horrible notation if you're working in three-dimensional space. It's really bad if you start working in arbitrary space. If you don't know how many dimensions, if you're working in an n-dimensional space, well, what do I use for my final letter? This is why we'll typically use E1, E2, E3, E4. Okay, so now let's just play our trick again. So here's I, V1, W1, J, V2, W2. And I will go plus signs that way and minus signs the other way. Okay? I'm going to try to avoid drawing the lines just so it won't be as messy on the board. The first one is the I direction. And I'm going to get V2, W3. And now this will be something with J, this will be something with K. This will be something with K, this will be something with I, and it will be a negative sign. So it will be minus V3, W2. So what I'm doing is rather than just writing out all the 6 terms, I'm just writing them, all the i's together, all the j's together, all the k's together. I'm just collecting the algebra. And lo and behold, look what we get. We get the first term, V2, W3 minus V3, W2. Now let's do the j term. So for the j, we'll have V3, W1. This is with a k, this is with a k, this is with an I, and this is with a j, so we'll have a V1, W3. All right, excellent. We're left with the k. So we'll have V1, W2. And now for the last one, we will have V2, W1. So this becomes a way to calculate the cross product of 2 vectors. You can memorize that formula, or you can memorize this trick to compute 3 by 3 determinants. You've really got to do one or the other. Now, there are a lot of programs like Mathematica which can actually calculate the cross products as long as you input your quantity with the right declaration. So sometimes if you use programming environments, you might mean to create something as a vector, but you might accidentally create it as a list, and then the system might operate on it incorrectly. So you sometimes just have to be careful how you declare your variables, how you declare your quantities. It's good to practice doing that. If anybody wants to, I'm happy to write up some notes on how to do that if you're having trouble. But there are ways to input matrices and vectors in Mathematica and have it do all the stuff for you. This doesn't mean that when you have a homework problem, you should just have Mathematica do it, but it means it's a great way to check and see if you got it right. Okay. Any questions on how to compute the cross product? So the cross product seems to be related to a determinant. Okay. What I want to do now is I want to change this, and this is the advantage of being at a blackboard, and I'm going to replace ijk with a third vector and just see what happens. All right. So this is the advantage of being on a blackboard. Any thought as to what I should call that vector? I've got VW. What should this vector be? U. Right? Try to always have good notation. You want to be able to look down and see what's going on. If I've got things going in an increasing order down here, I should probably decrease by 1. When the planet Uranus was discovered, does anybody know the original name of the planet Uranus, or the original proposed name? Have I mentioned this in class? It was originally in one of the greatest ass-kissing moments in the history of science. The person who discovered it named it after his monarch, King George of Britain. King of Britain loved the suggestion. The rest of Europe said, hell no. And so they said, well, since Saturn is the father of Jupiter, let's continue the trend, and we'll name the planet Uranus after the father of. And so they eventually accepted that. But really think about the notation you use. In calculus, what does a big F probably refer to? The integral, the antiderivative of little f. And that way, when you can quickly glance down, you can get some idea of the relations between things. So will have u1, u2, u3, u1, u2. And so now I have u1 here, I have u2 here, and I have u3 here. What does this look like? The dot product of what?
U and V cross W.
So this is U dotted with V cross W. So we get to use our two ways of combining vectors. V cross W is a vector, and I can dot that with another vector. The reason everything works so nicely in three-dimensional space is if I give you two vectors that aren't parallel, there's a unique direction perpendicular to both of them. Right? I'm in three-dimensional space. If I have two vectors that aren't parallel, there's a unique direction perpendicular to both of them. If I go into higher dimensions, that's not true. If I'm in four-dimensional space, if I take two vectors, well, I have an entire plane that's perpendicular to both of them. So one way of interpreting the determinant is it's u dot v cross w. So what we'll see in a moment is if v cross w is the area of the parallelogram spanned by v and w, v cross w, we've shown, is perpendicular to that plane. So then u dotted with that is how much of u is perpendicular to that. If u is parallel to that. Imagine u is in the same direction as v cross w. Then that would mean u would be perpendicular to this plane. And then that would mean for the parallelepiped that's coming out, you would be coming straight out of the blackboard, and it would be the height. Imagine u is not perpendicular to v cross w. Then we need to know what direction is in that perpendicular direction. And that's going to give us the height. So this will give us the volume of the parallelepiped. Okay? So there's a real geometric significance. If we can just show that v cross w is the area of the parallelogram, we're in great shape. All right, so now we need to figure out how to show that. All right, well, it's finally turned a little bit at least. Okay. So let's think about what's going on. So here's v, here's w, here's the parallelogram. How would you calculate the area of the parallelogram? So we know it's base times height. What do you want to make the base? Yes?
The magnitude of V.
Okay, magnitude of v. And then what's the height? So we might need to add more letters to this picture.
You do the difference of the y components of w and v. If you have.
That would only work, well, we've got to be careful because v is not aligned with the x-axis. So how would we find the height to the base? We would draw a line from where to where? We'd come down like this, and that would give us our height. So I want to relate this height to the length of w. What quantity do I need to add to the picture? Well, I could start adding the components, but there's another part of this picture that I want to label. I mean, if you have a triangle like this, if you know the hypotenuse and you know this is a right angle, what else do we need?
Angle.
The angle. Let's call that angle theta. And then this height would just be the length of w times the sine of theta, and that's the area. There is a limit to how much tedious algebra I want to do in public. At some point, I want to do enough so that you can then trust me that it works out. Have we seen anything related to theta in our history in this class? There's not that many lectures, so there's not that much to think back upon. What have we seen that's related to theta?
The
product.
The dot product. It's really nice at the beginning of the semester. There's not that many things to fall back upon. We've seen the dot product. So, like the politician who's asked a question, we want to work it to our favorite known quantity, the dot product. The dot product does not have a sine of theta. What does it have? How can I get from a sine to a cosine? What's their relation?
Derivative.
So one is derivative.
We do sine theta is the square root of 1 minus cosine.
So one is sine of theta is the square root of 1 minus cosine squared. Or you can do cosine, or you can do sine squared is 1 minus cosine squared. It's better not to have a square root. And so if we look at the area squared, we get the length of v squared, length of w squared, sine squared theta is the area squared. This is the same as the length of v squared, the length of w squared, 1 minus cosine squared theta. Okay. So now, what do you want to do with the 1 minus cosine squared? What can we do for cosine squared? So area squared is length of v squared, length of w squared. And how should I substitute for cosine?
Using the dot product formula.
Yeah, so what would that be?
P dot Q.
So here it's going to be v dot w
P dot W
over.
over the length of V times the length of W.
But now we have to square everything. Right? So now we get area will be the length of v squared, length of w squared, minus v dot w squared, because those will cancel. Okay? It turns out that this is the length squared of v cross w. Yes?
Wouldn't that be area squared?
Ah, yes, it should be area squared. Thank you. So how would you show that this is the same as this? How would we show this? Yep. It's called rolling up your sleeves and just doing the algebra. You put in v1, v2, v3, w1, w2, w3, take the dot product, square things, subtract, simplify, and then compare that to, oh Lord, now we'll have those differences, we'll square those, take all the cross terms, and then just do a lot of algebra. And when the dust settles, we end up with the cross product formula. So the vector v cross w, the magnitude is the signed area, and the direction is perpendicular to the surface. This is going to be very useful, especially for people who are doing physics, when you want to talk about motions of objects. You might have objects that are constrained to lie on a surface. And so maybe you're constrained to lie on the surface of the Earth, or maybe the surface of a football. And you might want to figure out, what are the possible directions you can go and stay on the surface. Those will be tangents. What direction can you go where you'd be perpendicular to the surface? That would be the normal to the surface. This is a heads up for what's coming later in the semester. The big concept in Calc 1, Calc 2, was to replace a complicated function with a straight line. Right? in Calc 1, the goal is to replace a function with a straight line. Lines are easy to understand. If we have a function of 2 variables, instead of approximating it with a straight line, what do you think we're going to approximate it with? Yes, a plane. And if we had a function of 3 variables, we'd approximate it with a hyperplane. And so the whole point of something like this is to give us a sense of what is the direction that's perpendicular to the hyperplane. So the next section after this, we're going to get into equations of lines and then equations of planes. And we can use a lot of stuff like this to very easily figure out what's going on. So unfortunately, a lot of times there's just algebra you need to do. Could my kids do this? Cam in 5th grade, probably. You know, they still haven't really learned FOIL yet, so I'm not 100% sure. But with a little bit of help, I think they could. Would they want to do that? No. Do you want to do this? No. It should be done once, or you should look at the book and see where they go through the algebra so that you're convinced that it's true. But this is the cross product, and this is one of the reasons why we care so much about it. It gives you a vector with extremely useful information. As an aside, the book remarks that this can also find the area of a triangle. If you have 2 vectors, the area of the triangle that you get by connecting this is just 1/2 the cross product. I am not going to write the following down on the board because I think it's just too stupid. The book also says this gives you a test for whether or not 2 vectors are parallel. Check and see if their cross product is 0. What does it mean for 2 vectors to be parallel? Yes? One is a scalar multiple of the other. So if one is in this direction, then the other must be 5 times that, or 1/3 times that, or pi times that. Which would you rather do? See if all the components are in the same ratio, or take the cross product? I would probably rather just see if they're in the same ratio. But if you want to check and see if 2 vectors are parallel, absolutely welcome to use the cross product. Okay, so the hardest part is, and this was one of the questions someone had asked, was understanding the direction of the cross product. And this is somewhat hard to really explain without linear algebra. But we saw that when we looked at this 3x3 matrix, the UVW, we got the volume of the parallel pipette. If we can assume that that's what the determinant gives. So in a linear algebra class, you'll learn that the determinant gives you the volume of the hyperparallelogram spanned by those vectors. And so when we see the dot product like that, we can see that this is giving us the component that's perpendicular to the surface spanned by V and W. That's where the direction is coming from. All right, so if we want to calculate things, we now have formulas to calculate things. So if I want to take the cross product of 2 vectors, so let's say V is 2, 7, 1, and W 8, 2, 8. All right, in honor of E. So if I want to calculate V cross W, I divide I, J, K, 2, 7, 1, 8, 2, 8. Now write I, J, K, 2, 8, 7, 2. I don't need to do it twice. All right? And so I now go through, and for my I, I'll get 7 times 8, and I'll get minus 2 times 1. So do you want me to go through all 6 terms, or do you want me to just collect the terms immediately? First one to speak wins.
Just collect the terms immediately.
All right, so the I will be 7 times 8, and then the other I is in this direction, will be 2 times 1. So it'll be 7 times 8 minus 2 times 1. The J will be 1 times 8, and the other J will be 2 times 8. And then the K will be 2 times 2, and the other K will be 8 times 7. So we would get 56 minus 2 is 54. 8 minus 16 is negative 8. And we would get 4 minus 56 is minus 52, if I have done the algebra correctly. Okay? Yes?
Is the reason that you have I, J, K there because they're placeholders of 1 and it just works as a 3, like when it's a 3-dimensional?
So what we're doing here is highly illegal. So when you calculate a determinant, you should be putting numbers in everywhere. We're putting vectors in these components. So we saw that when we had V and W and we put in a U here, we ended up getting U dotted with V cross W. So you can view this as a placeholder and saying that the stuff that hits this is supposed to go in the first component, the stuff that hits this into the second component, and the stuff that hits this is into the third component. You can also just remember the formula that the first component will be V2W3 minus V3W2. The next component will be V3W1 minus V1W3. And the third component will be V1W2 minus V2W1. You can remember it either way. I think this is a little bit easier to remember, but either way is absolutely fine. What do you think V cross W would be? And is it clear what that means, or do I have to put in parentheses? Is it clear what this means, or do I have to put in parentheses?
You have to put in parentheses.
All right, so let's cross these two first. So what do you think V cross W would be? Why 1?
Because they're perpendicular and sine of theta is 1.
What do you know about the vector V cross W?
It's going to be perpendicular to both V and
It's going to be perpendicular to both V and W. So do you think that when I cross this with V, I'll get something that's non-zero? If I take generic vectors, would you expect to get something that's not 0? I'm now crossing V with something that's perpendicular to V. Yes?
Would it be in the same direction as W? Because it should be, we're taking a vector that is already perpendicular to both V and W.
Right.
And then we're finding a vector that is perpendicular to that. So wouldn't the direction of that vector be the same as W?
So how could you check and see if this is perpendicular to W?
Plug and check.
Plug and check. Take the dot product with W. It seems quite possible that it will be perpendicular to W. I'm not going to go into that right now. This is a nice conjecture. But do you think that this should be non-zero? If I choose generic V and W. So V and W are not aligned with each other. V cross W will be something. It's perpendicular to V. So this is going to be the length of V times the length of V cross W times the sine of the angle between them. And the angle between them is 90. So I would expect that this would be non-zero. What if I grouped it the other way? V cross W. What would you expect that to be? That would be 0. Because V cross V will be 0. So this is a proof that order matters. So the cross product, it's not commutative. It's also not associative. The way you group things matters. So it turns out I cross J is K. J cross K is I. And K cross I is J. And they often refer to this as the right-hand screw rule. So that you start with your thumb up, that you curl your fingers from the first vector you're crossing to the second. And then your thumb points in the direction of the cross product. What would happen if you tried to use your left hand? You'd have to be curling from the second vector to the first. Right? Can you use your left hand? Absolutely. Right? This is just supposed to be a mnemonic for you to get a sense of which direction things go. So if you start with V and cross it into W, your finger will point in the direction of the cross product. So when you look at I and J, it points up into the Z-axis. When you look at J and K, it'll point into the I-axis. What's J cross I? That'll be negative K. So this is going to equal negative J cross I. It's not turning at all. I might have to move back to the... All right. All right, so we've got about 2 or 3 minutes left. Any other questions on this section? What have we not done so far, really, this semester that you would have expected to do in a calculus class? Calculus, right? The calculus is coming. What we're doing right now is we're building up the notation, we're building up some of the preliminary results that will allow us to write things down. One of the things that's going to be a real challenge is generalizing some of the results from one dimension to higher dimensions. Sometimes when you're in one dimension, it's not really clear what the higher dimension analog will look like. How many of you have seen Taylor series? Okay, how many of you have not seen Taylor series? Okay, you are not supposed to have seen Taylor series if you're in this course, so do not worry if you haven't seen them. It's basically a way to expand a function in terms of its derivatives. And the more derivatives you know, hopefully the better sense you have of the function. It turns out it's a little bit interesting to try to expand that into high dimensions. All right, since we have about 1 minute left, I will tell you about the bet I made one day in grad school. I was walking to the office with 2 of my friends, and we were talking somehow about Morley's theorem. I believe the observation goes back to the ancient Greeks, but the proof wasn't discovered until, I think, sometime in the last 200 years. So take any triangle, trisect each angle. I'm just going to approximate things, I hope. Okay. And for each trisectors, for each side, look at the 2 trisectors that are closest to it. And you get 3 points. Connect the 3 points. What can you tell me about that triangle?
Is it similar to the triangle?
Good guess, but no, it's not similar. It is a special type of triangle.
Is it equilateral?
It is equilateral. No matter what triangle you start with, it's equilateral. And I said to my friends, the proof is obvious. It's trivial. How do you do it? I said, well, you make this point 0, 0. You make this point 1, 0. And then you just write down the coordinates of the 3 points and show that the squares of the lengths are equal. And so one of my friends bet me not that I couldn't, but that I wouldn't have the patience to complete the proof before we got our PhDs. Took me about 1.5 years. I did not work on it solid. If you use like the tangent of 1/3 of the angles, it's not so bad. You keep squaring things and cleaning up denominators. I was allowed to use Mathematica to expand things. I end up with, I think, polynomials of degree 48 and 2 variables. And I just expand everything out, and then I subtract one side from the other, and all the terms vanish. And that's a proof. At the end of the day, do you have any understanding why Morley's theorem is true? No. The best proof I know is due to John Conway, where he starts off with an equilateral triangle and reverse engineers the original triangle. It's beautiful proof. So my friend bet me a dinner not to exceed $12.50 if I could do it. If I couldn't do it, I had to get him an ice cream not to exceed $2.50. So I still have the receipts from those in my office to remind me, just because you can do something by brute force doesn't mean that that's the way you should do it. Sometimes it's the only way we have, but if possible, you really want to get a sense of why something is true. That's why I've been spending so much time in the beginning explaining, here's motivation. Here's the special case of the cross product when one of the vectors is along the x-axis. That's where these formulas are coming from. All right.